Bismillahirrahmanirrahim, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will explain singular value decomposition. So, the definition of singular value decomposition is that if we decompose a system matrix A into three matrices, then that decomposition is called singular value decomposition. And in previous lectures, we studied LU decomposition or LU factorization, and in that method, we actually decomposed the system matrix A into two matrices, L and U. L was the lower triangular matrix, and U was the upper triangular matrix, and the product of these two matrices was equal to the original matrix A. In singular value decomposition, we will evaluate three matrices, and the product of those three matrices will be equal to the original A matrix. So there are some assumptions which we have to consider while evaluating the singular value decomposition of a system matrix. And the first assumption is that the U matrix is an orthogonal matrix, and V matrix is also an orthogonal matrix. And the system matrix A can be evaluated by multiplying the three matrices U, sigma, and V transpose. So first matrix is the U matrix, second matrix is the sigma matrix, and third matrix is the V transpose matrix. Now this U matrix is an orthogonal matrix. This V matrix is also an orthogonal matrix. And the definition of orthogonal matrix is that if we multiply the transpose of one matrix with the original matrix, and if we get the identity matrix as a result, then that matrix is called as orthogonal matrix. So in this case, U matrix is an orthogonal matrix and V matrix is also an orthogonal matrix. So U transpose multiplied by U is equal to identity, as well as V transpose multiplied by V is also equal to the identity matrix. So first of all, we will evaluate A transpose multiplied by the A matrix. So this is our A matrix. So the transpose of A matrix will be equal to the product of these three matrices and the whole transpose, and this is our original A matrix. So let's evaluate the transpose of the product of these three matrices, and that will be equal to V transpose whole transpose multiplied by sigma transpose multiplied by U transpose. Because if we evaluate the transpose of a product of matrices, then that will be equal to the transpose of the last matrix multiplied by the transpose of the first matrix. So the order actually changes. So V sigma transpose into U transpose multiplied by U multiplied by sigma multiplied by V transpose. And we know that U matrix is an orthogonal matrix, so U transpose multiplied by U will be equal to the identity matrix, and that will be equal to V sigma transpose multiplied by sigma multiplied by V transpose. So this is actually our A transpose multiplied by A matrix. Now, from our previous lecture, we know that a matrix can be written as S lambda S inverse, right? So if A is equal to S lambda S inverse, now we can say that this first matrix is equal to the matrix of eigenvectors of A. This second matrix is the matrix of eigenvalues of A with the eigenvalues at the diagonal. And this last matrix S inverse is actually the inverse of the matrix of eigenvectors, which is our first matrix. So S inverse is the inverse of the first matrix. Now, if we compare this expression or this equation with this equation, here A transpose A is equal to V sigma transpose sigma multiplied by V transpose. So we can say that if we evaluate the eigenvectors of A transpose A, and the matrix of those eigenvectors will be our V matrix, and sigma transpose multiplied by sigma. So the new matrix as a result of this product will be our matrix of eigenvalues as we had in this example, right? And here we had capital lambda in between, and that was actually equal to the matrix of the eigenvalues of A with eigenvalues at the diagonal. And this last matrix should be equal to the inverse of the first matrix. Since V matrix is an orthogonal matrix, So V transpose is equal to V inverse, right? V transpose is equal to V inverse such that V transpose multiplied by V is equal to identity. So this V transpose is equal to V inverse, and we can say that the matrix of eigenvectors of A transpose A is actually our V matrix, and then we will evaluate the eigenvalues of A transpose A, and we will get sigma transpose multiplied by sigma, and that will be our diagonal matrix. So the transpose of the diagonal matrix is equal to the original matrix. It means we can evaluate sigma square matrix, and if we evaluate the square root of the diagonal entries, we will get the sigma matrix. So V matrix and sigma matrix, these two matrices will be evaluated by just evaluating the eigenvalues and eigenvectors of A transpose A, and then we are left with the last matrix, which is our U matrix. So we are given the A matrix, right? It will be given to us, which you can see over here. And we have evaluated this V matrix and this sigma matrix. So we can evaluate the U matrix from this expression, right? So A is equal to U sigma V transpose, and let's multiply this equation with V from the right hand side. So AV will be equal to U sigma V transpose into V. So AV is equal to U sigma V transpose into V. Now V transpose into V will be equal to identity. So AV will be equal to U sigma. So now we are left only with this U matrix. A matrix is given to us. We have evaluated this V matrix and this sigma matrix. So U matrix can be evaluated. Now let's solve this very simple example in which we are given this A matrix and we have to evaluate V matrix, sigma matrix, and U matrix step by step, and then we will get our answer. Now A transpose multiplied by A will be equal to this matrix. Just evaluate the transpose of this matrix and multiply that matrix with A, right? In this order, A transpose A, right? So that will be the resultant matrix. Now we can easily evaluate the eigenvalues of this matrix. So eigenvalues are equal to 20 and 80. This is first eigenvalue, this is the second eigenvalue. Similarly, we can evaluate the eigenvectors of A transpose multiplied by A. So this is our first eigenvector V1, which is equal to minus 3, 1. And this is our second eigenvector V2. And we have to normalize our eigenvectors. So eigenvectors should be in the form of unit vectors. So these are the vectors. So let's convert them to the unit vectors. And unit vectors can be evaluated by dividing the vector with its magnitude. Now the magnitude of this vector is equal to minus 3 square plus 1 square under root. So that will be equal to 10 under root. So let's divide minus 3 by 10 under root and 1 by 10 under root. So this is our normalized eigenvector V1. Similarly, the normalized second eigenvector V2 will be equal to 1 over 10 under root and 3 over 10 under root. Now the matrix of eigenvectors V will be equal to V1 and V2. This is our V1 and this is our V2. So this is our V matrix. Now we can evaluate the sigma matrix. Sigma 1 and sigma 2 are the square roots of the lambda 1 and lambda 2 respectively. So sigma 1 is equal to 20 under root. This was lambda 1, and sigma 2 is equal to 80 under root, and these can be written as 2 square root 5 and 4 square root 5. Now you have to remember that the matrix of eigenvalues of A transpose A is equal to sigma transpose multiplied by sigma. So that is actually equal to sigma square. Since sigma is a diagonal matrix, so sigma transpose multiplied by sigma will be equal to sigma square. So we have to evaluate sigma matrix. So then we have to evaluate the square roots of the eigenvalues of A transpose A. So that's why we have evaluated the square roots over here. And this is our sigma matrix. So 2 square root 5 and 4 square root 5 at the diagonal, and these are the off diagonal entries which are equal to 0. So two matrices have been evaluated. Now the last matrix, which is the U matrix, can be evaluated from this expression. AV is equal to U sigma. Okay. So this is our AV matrix, right? So this is A, this is V. So the product of these two matrices is equal to minus 10 under root, 2 10 under root, 10 under root, and 2 10 under root. And we have to divide this matrix with the sigma matrix, or we can say that uh, U matrix is equal to AV sigma inverse, right? So this is AV matrix, and if I multiply this with this sigma inverse matrix from the right hand side, we will get our U matrix. So this is one way of evaluating this U matrix. Now the inverse of this sigma matrix is equal to 1 by 2 square root 5 and 1 by 4 square root 5, and these entries will be equal to 0. Since this is a diagonal matrix, so the inverse of this matrix is actually equal to the reciprocals of these diagonal entries. So that will give you the inverse of this matrix. So 1 by 2 square root 5 and 1 by 4 square root 5 will be the inverse of the sigma matrix. Just multiply that inverse with this matrix at the right hand side, then you will get your U matrix. So this is our U matrix, and that method will be the simplest method. So this is our U matrix. Conversely, you can multiply this U matrix with this sigma matrix, and then you will be getting this AV matrix, the product of A and V matrices. So that is another way of evaluating this U matrix. But I will recommend you to evaluate this U matrix by first evaluating the inverse of the sigma matrix, which is equal to 1 by 2 square root 5 and 1 by 4 square root 5 and 0, 0 over here. And then multiply that sigma inverse matrix with this AV matrix from the right hand side. So this is AV matrix, and here you will have sigma inverse matrix, and then you will get your U matrix. So if we multiply these three matrices together, this is our V matrix. Sorry, this is our U matrix, this is our sigma matrix, and this is our V transpose. If you multiply these three matrices, you will get this original matrix here. So this is called singular value decomposition. And I hope that this lecture was quite understandable to you, and you have enjoyed solving an example on singular value decomposition. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.